In this tutorial set, we'll be looking at the overall general principles with the use of the CNC machine, in addition to the Rhino plugin software known as RhinoCam. The objective of this set is to provide a rudimentary level of understanding with regards to the workflows and software skills needed in order to execute tasks using the CNC machine. CNC, defined as Computer Numerical Control Manufacturing, is a subtractive technology that removes material from a defined geometry, more so known as stock, blank, or workpiece. The workflow that occurs in the process of CNCing a geometry is as follows. The user/designer creates a 3D digital geometry that is intended to be cut. Once the model is complete, it is then sent to a CAM software, such as RhinoCam, to then be evaluated and converted into G-code. G-code is a language that is read by CNC machines, in which it dictates the location at which the spindle needs to be, the speed at which the tool revolves, and many more additional parameters. Once the G-code is completed, the CNC machine reads and then executes the operation. The CNC that is currently used in the Ryerson Department of Architectural Science workshop is a 3-axis CNC machine. This means that it operates in the following axes relative to the stock: left, right, up, down, and forward and backwards. When designing for the CNC machine, the following precautions need to be taken into consideration: tool geometry, tool axis, tool stiffness, and stock dimensions. The tool geometry needs to be considered as it is the tool that will be defining the overall finish of the cut product. Certain tools will need to be used in order to achieve different types of finishes. An example of this being the use of a ball mill tool bit to remove material to achieve a smooth finish on a contoured surface. Tool axis is defined by the reach of the tool bit to the specified surface to cut from. Due to the CNC machine being 3 axes, tool axes such as undercuts are not possible to achieve unless particular tool bits are used. It is important to evaluate the geometry that is being cut in regards to the tool axis, as portions of the stock might unintentionally be removed during the CNC process. Tool stiffness should be considered in regards to the ratio of the tool diameter to the depth at which it is cutting material. Additionally, the dimensions of the tool itself inside the tool holder will also have an effect on the tool stiffness. What can result is the tool snapping or vibrating and deflecting, reducing the accuracy in the stock that is being cut. Stock stiffness should be considered in relation to the amount of material that is being removed. With the stock being suctioned down to the bed of the CNC, the surface contact of the stock is important to maintain. Any reduction in the contact can result in an unsteady workpiece, which can reduce accuracy in the cut. To remediate this, consult with the workshop staff to attach a jig to the CNC bed. Another aspect in regards to the stiffness of the stock is the material brittleness and strength. Minimum thickness should be consulted and prototyped to ensure that the stock won't snap or deform during the CNC operation. Stock dimensions should be evaluated before designing the material to be cut. Parameters such as max depth that the stock is being cut in relation to the boundaries of the stock will affect the type of tool bits that will be used. This will inevitably dictate the overall depth at which the stock will need to be in order to achieve the desired cuts. If not coordinated correctly, this can result in undesirable cuts, wasted stock, or loss of time to redesign the stock to fit the constraints of the bed. It is recommended that new users to the CNC machine coordinate their time to abide by a certain workflow to ensure a successful and efficient CNC process. Before prepping a CNC file, students should consult with the workshop staff in regards to, all but not limited to, their design ideas for CNCing, the appropriate material choice for the stock, ideal dimensions for the stock, overall assembly of the cut material, and workflow of the design and execution of their CNC'd object. Students will then be required to purchase or acquire their stock material and form it to the recommended dimensions of what the stock should be. This may require adhesives to enlarge the stock by layering it, or to reduce the stock by removing excess material through the workshop resources. It is recommended that before the intended day of CNCing, the students consult with the workshop staff to review the 3DM file to be cut. The objective of this is to review the proper toolpaths, detect any collision errors, and to provide the workshop staff with a notice to load and configure the proper tools for the intended cut. This will ensure that the money spent on CNCing will be used to its maximum potential for the cut, and not wasted on prepping the machine. Lastly, while the CNC machine is operating, it is up to the student to monitor the machine and to not leave it running unattended. If an error in the machine or the file occurs, notify the workshop staff to assist. This is to ensure that any damage to the machine or to the stock that is being cut can be remediated and hopefully avoided. While stock is being rotated in between cuts, clean up the bed by removing excess material waste on the CNC machine and around the area of the stock. This will diminish any problems with the CNC machine and reduce inaccuracies on the stock due to scrap materials being in the way. Once the CNC job is complete, clean the area around the machine thoroughly. It is important to clean the space as it was initially found. This will ensure that the workshop staff can focus on their time on helping students rather than cleaning up, and it will allow the following CNC job to be completed effectively and efficiently.